Hey everybody, happy Tuesday to you. We are going to continue working on ellipses. I've got just a couple new things for us to look at today, and then we'll switch over to the last topic for this class, which is hyperbolas. That'll be Thursday and Friday's lesson, and then wrapping things up for you guys next week. Ellipses, we want to take a look at how the definition describes its shape. That's something that I alluded to in the Monday lesson, but we didn't really talk about it, or we didn't get very far into it. And then we need to make sure we can understand how to find where vertices. I don't think I used the term co-vertices, but I'll make sure I clarify that today. And then also the foci. Foci is plural of focus. We'll find one focus and then know where both foci go. Um, my definition of a circle, which is old news at this point, but it's all the points that are equidistant from a fixed point, whereas an ellipse is all the points in a plane such that the sum of the distances to the two fixed points, which we call foci, is always the same. In other words, if these two red dots are the foci of this ellipse, the sum of these two lengths will stay constant. So one of the ways that you could draw an ellipse, and you can go ahead and do this. If we were doing this together, I might have passed out a bunch of string and or whiteboard or dry erase markers for you to try drawing this on your desk. But take a string, and you might need someone to help you with this. Hold down two ends of it, some distance apart that is less than the length of the string, and then put a pencil like I've got it here. Pull it nice and tight, and as you draw around, the shape that you make is called an ellipse. And so these two distances, these two lengths will always be the same in a given ellipse. I thought I should probably give you all of the terms on one slide so you can take a look at these and know what I'm referring to when I talk about a vertex or a covertex. A vertex, there's another one over here. These are the 2 points that are the farthest away from the center. The covertex are the 2 points that are closest to the center. The major axis is the distance between your vertices. It could be the horizontal axis or a vertical axis. In the case of the ellipse I've got right here, it is a horizontal axis. And then the minor axis is the distance between the covertices. And then finally, the focus. Each of these is a focus. I've got two foci. And the property that these points have is that any point on this ellipse, the sum of these two segments is the same, regardless of where I am on the ellipse. And it's not going to be a big deal for us, but that's called the focal constant, is the sum of those two segments. We saw yesterday the standard form of an ellipse: x minus the x value of the center squared over something squared plus y minus the y coordinate of the center squared all over something squared equals 1. And if we've got something that's in this form, we saw yesterday that the center of this circle is h comma k, again coming from these two values, similar to what we saw with a circle. And we also saw yesterday that the square root of this, the denominator on the y term, gives you the length of your vertical distance to the ellipse, and then the square root of the denominator of the x term gives you the horizontal distance from the center to the ellipse. In the case of the one we're looking at right now, again, the horizontal axis is the longer one, so that would be the major axis. The 2 points, the 2 endpoints farthest to the left and to the right would be called the vertices, and then straight up and straight down, that's our minor axis because it's shorter, just happens to be vertical this time, and then the 2 points there would be the co-vertices. All we have left to do is to figure out how to find where the foci go. And so this is a little bit tricky for me to try to explain. I'll give you the formula. The formula is going to be a pretty easy formula, but where the formula comes from is a little bit trickier. I'm going to imagine this. So this red path, I've got a blue path, I've got a black path, I've got this red path. All three of these paths are the same distance if these 2 points are foci. So if I'm if I measure this length and then that length, that is my focal constant. That would be the same as these two or the sum of these two. But imagine, I'm going to, let's see, I'm going to choose, I guess I'll make this a dotted line. Imagine if I had a different path that goes from one focus to another one, where this path, I'm first going to go straight up to the top, to the vertex, and then straight down through the center to the other focus. Now that distance, that total distance up to the top and then down to the second focus is the same as the distance right here along the red one or the blue one or the black one, but I'm going to focus on the red one as I try to justify this. That distance is going from the focus to the edge of the ellipse and then repeating that distance and then the distance between the foci. And if you think about taking one of those dotted line sections up here and moving it down to the bottom, we see that the distance all the way across this, the length of the major axis, is also that focal constant. In other words, the distance all the way across this would be the same as the distance out to the co-vertex and then back to the focus, which means that half of this length, the length from the center to the vertex, is the same as the length from the focus to the co-vertex. Now, whether or not you understood that, what that means is that, yes, A is the horizontal distance, B is the vertical distance to the ellipse, but that section of the major axis turns out to be the same as that segment from the focus to the co-vertex. And the reason this is significant is because that gives us a right triangle. And whenever I have a right triangle, the two axes are perpendicular to each other, I've got the Pythagorean theorem. Now, you probably memorized the Pythagorean theorem as a squared plus b squared equals c squared, but that was in the case where a and b were the legs and c was the hypotenuse. For the case of the one that I've got here, a squared plus c squared equals b squared, and then we take the square root, or do a little bit of algebra to solve for c, and we get this. This is our formula for finding the length from the center to one of the foci. It comes from the Pythagorean theorem. Now, if none of that made sense, if you want it to make sense, go back and watch it again, maybe slow it down, pause it to think about stuff. If you just want to make sure that you do well on the test or the quiz, here it is. To find the distance from the center to one of the foci, from the center to a focus, it's just the square root of either b squared minus a squared or a squared minus b squared. It just depends which one's bigger. If you've got an ellipse that's longer or taller than it is wide, then you do b squared minus a squared. If it's wider than it is tall, then you do a squared minus b squared and take the square root. But really, just take the big one minus the small one and you're going to be just fine. And that is how we do it. So I'd like to go through two examples for you today, and actually your homework tonight, I believe, is only two examples, and they're pretty similar to the ones that I will be doing today. So hopefully this will help you with the assignment. Hopefully this will help you understand what we're doing. I would like to find where the center, the vertices, and the foci are for this ellipse. Here's our standard form: x minus something squared over something squared plus y minus something quantity squared over something squared equals 1. So that 36, that's a squared. Oops. And if 36 is a squared, that means a is 6. Our horizontal distance from the center to the ellipse is 6. And that 16 in the denominator of this one means that b is the square root of 16, which is 4. And so that's our vertical distance. So this ellipse is going to be wider than it is tall because the vertical axis is larger than the horizontal axis. And so no problems there. We can also identify the center from the general form. I've got x minus the x value. Well, let's see, x minus negative 3 would be the same as x plus 3. So x minus negative 3 is what we're looking at here. And then y minus the y value. So the y value is 7. And so now if my center's at negative 3, 7, and my a is 6, that means that I can go either to the left or to the right of that center to get my vertices. And so let's see, if I'm moving left and right, my x value is changing. So it could either go down by 6 to get to -9, or it could go up by 6 to get to +3. And so those are my vertices. Again, the ones that are farther away are the vertices. Co-vertices, in this case, are going to be up and down. And because my value of b is 4, I'll be going up or down by 4 spots. So now my x value stays at the place where the center was, and I will increase by 4 to get up to 11, or decrease by 4. Let's see, 7 minus 4 is 3. And so those are my co-vertices. And then finally, to find where my foci are, first of all, I know that they're going to be along my major axis. This ellipse is wider than it is tall, which means my foci are going to be on the horizontal axis for this one, because 36 is the larger of the two values. And to find what that distance is, c is equal to the square root of, I'm just going to take the bigger one squared minus the smaller one squared. And remember that this is b squared. So b squared is 36, excuse me, that's a squared. And then 16 is b squared. Again, it doesn't really matter if you call them a or b, but take the bigger one minus the smaller one, and we end up with the square root of 20. And I don't know exactly what that is. It must be 4 point something. Square root of 20, I'm just plugging into my calculator and finding that it's about, I'm going to call that about 4.5. It's 4.472. So now at this point, I found everything that I need to find. And so now if I want to graph this, let's see, -3, 7 is up there. There is my center. I should have written down these over here, but I'll be able to do this anyway. My a value is 6, so I go to the left and to the right by 6. My b value is 4, so I go up from that point 4 and down 4 to get to those points. 1, 2, 3, 4, 1, 2, 3, 4. And then finally, my c value, the distance to the focus, to both of the foci, is about 4.47, about 4.5. And so those, again, will be on the horizontal axis because this ellipse is wider than it is tall. 1, 2, 3, 4, about 4.5. There is one focus, and the other focus is over on the other side. I'll try to sketch this as usual. I'm sure this will be a little lumpy, but at least mathematically fairly accurate. So now if I've done a good job of this, and I haven't done a great job of this, but if this is an ellipse, then this distance would be the same no matter which point I choose on the ellipse. So there we go. That's finding the center, vertices, and foci and graphing it. And you may say to yourself, well, why would I bother with another question? Because that covered everything. But one other piece that I need to cover is, what if it doesn't come in standard form? What if we have to do a little bit of manipulation first? And so actually the only tricky part of this one is going to be the first step, and that is taking something that looks like this and switching it around into something squared over a number plus something squared over a number equals 1. And so I guess, I don't know if it's really a trick, but I'm going to call it maybe a technique instead, is to look over here. This needs to be equal to 1. And so if it's equal to anything other than 1, let's just divide by that. Let's just divide everything by 225. And we'll see what happens when I do that. Now 9 divided by 225, I don't know if that's very obvious what that is, or 25 divided by 225. But it turns out, partially coincidentally, partially not so coincidentally, mostly I wanted to make sure that this problem worked out, 25 over 225, well, 25 goes into 225 9 times. 9 times. So if I cancel out 25, we'll be left with x minus 5 squared over 9. And if 225 divided by 25 is 9, then 225 divided by 9 is going to be 25. And so that gives us our a and b values. Also, we can tell by looking at this what the center of the circle, or excuse me, the ellipse is. Um, my major axis now is the vertical axis. It's the square root of 25 is 5. So the distance from the center to the vertex will be 5, and it's straight up and down. Square root of 9 is 3. So to the left and to the right, we'll go over by 3 to get to those points. And then I guess let's find the focus also, as long as we are working on this. I'm going to be smarter this time. I'm going to put the center and vertices and the other stuff on my next slide with my graph. But I'm going to find what my distance to the focus is. And again, my general form, it's either 9 squared minus 25, 9 minus 25, or 25 minus 9, a squared minus b squared, or b squared minus a squared. Take the big one, 25. So b squared minus a squared, 25 minus 9 is 16, and the square root of 16 is 4. So this one's actually a pretty nice number. So I'll start with the center. Let's see, the center, I've got x minus the x value, x minus 5, so 5 is the x value, y minus the y value, y minus -1 is the same as y plus 1, so there is the center. My vertices, I got to be careful on this one. My major axis is vertical because my denominator is larger for the y term, so I will be going up by 5 and down by 5. So my x value stays constant. I will go up to 4 or down to -6. So those are my two vertices. And I guess I could start graphing these. 1, 2, 3, 4, 5, -1. So there's my center. Up 1, 2, 3, 4, 5 from there. Down 1, 2, 3, 4, 5. That's 5, 4, and 5, -6. My co-vertices, now I'm looking at the a squared value. And so I will go either to the left 3 or to the right 3. Adding 3 to 5 gives me 8. Subtracting 3 from 5 gives me 2. And so those are my co-vertices, counting off 3 to the left and to the right. 1, 2, 3, 1, 2, 3. Looks good. And then my foci, I found them by value of c was 4. And I can see that this ellipse will be taller than it is wide. So I'll count along the vertical axis, 1, 2, 3, 4. There's one focus. And down, 1, 2, 3, 4. There is the other focus. So the coordinates of those 2 points are 5. Let's see, I moved up 4. -1 plus 4 is 3. And down 4. -1 minus 4 is -5. And so there we go. There are my foci. I wonder if I've got a tool that'll just draw an ellipse. Let's see if I can make this work. Oh, there we go. I'll go with that. Much better than me trying to freehand it. So there we go. That is how to figure out all the properties of ellipses. We're going to find out that hyperbolas are actually similar to ellipses, but there's a little bit more pickiness with those. But I'm going to save that for Thursday. Hopefully you're having a great penultimate week of school, and we will see you later. Bye-bye.